do a quick overview of Chapter 8, Potential Energy and Conservation of Energy, the key equations at the end. And what we're looking at here is we have the potential energy U. And so you need to think of this as U going from some state A to some state B. And so the change in potential as you go from A to B is just potential energy at state B minus potential energy at state A. And this is equal to the opposite. This is a negative of the work done in going from A to B. State. And I say state here because that's more general than point. In going from one point to another, it simply looks like this, right? The change in potential energy is the potential energy at the point you've arrived at minus potential energy at the point you started at. And so that's the very specific positional change. An example of positional change would be potential energy due to gravity. And so you go up in a gravity well, go down in a gravity well, and this is near the Earth's surface. So it's just mgy plus some constant, right? Because you can define y to z equals 0 to be wherever you want. And there's some offsetting constant at that point. That is your potential energy at that point. Potential energy of an ideal spring is 1/2 kx squared. This x is the distance the spring is deformed from its rest position. So it's not the length of the spring, it's how far it's deformed for its rest position. Positive x is stretching the spring, negative x is compressing the spring, and it's just simply the distance from that. This constant k is the spring constant, that is in newtons per meter. So when you take newtons per meter and multiply by meter squared, you get a newton meter, which is a joule. Work done by conservative forces over a closed path. Right? You go over a closed path with conservative forces only, and you get 0. This is like, what is my change in potential energy as I walk around a mountain and come back to where I started? Well, the change is 0. And for every up I did a down. And so I add potential and I subtract potential as I move around, and eventually come back to where I started, and that's a total of 0. If conservative forces are conserved in 2 dimensions, then their derivatives with respect to the other dimension are equal. So dfx dy equals dfy dx. Conservative force is the negative of the derivative of the potential energy. So the direction of increasing potential energy is negative force. The direction of decreasing potential energy is a positive force, i.e. gravity pushes you, gravitational force is down, not up, right? Okay. And finally, conservation of energy. There are a couple of ways to think about this. You could do Ki, my great handwriting here, plus Ui, and plus, I'm going to go ahead and put in here work from non-conservative forces equals Kf plus Uf. And so, as I've written it, your initial kinetic energy plus your initial potential energy plus work done by non-conservative forces in going from your initial state to your final state equals your final kinetic energy plus your final potential energy. This simply says, hey, we're taking this and saying it's 0, right? And so once you take that out, then the change in kinetic energy plus potential energy equals 0. The distribution among them may have changed. You may have more kinetic, or you may have more potential and less of the other. But the total change in energy, if there are no non-conservative forces, is going to be 0. All right, that's it for the overview. We'll get into the problem shortly.